I just want to make some comments, basically, sort of about general relativity and about black holes and about black hole evaporation. So there are going to be about 4 different connected but different things that I'm going to mention. First one I want to say is that black holes form. So there's been a steady stream over the last 30 or 40 years of people who continually talk about, well, perhaps black holes don't form. We have people like Mottola, Visser, Mather, various and sundry people have come along and said that black holes, maybe something quantum mechanical goes on that means that black holes don't form. We have Einstein's equations. And Einstein's equations, we believe, I mean, they've been tested very well, on scales of the solar system. We also believe, because Newtonian physics works so well, that this goes down to the scales of millimeters or sub-millimeters, that as long as one is in that kind of scale, as long as the radius of curvature of the space-time is much larger than the Planck scale, that these equations behave pretty well. Well, what does this mean? So let us imagine that we've got this situation where, let's consider a system here where this would be the horizon of the black hole. Well, let's erase that and let's have some matter falling in here. And so this is the conventional picture. Now, the picture that they want is that for some reason or another, as this stuff gets near that horizon of the black hole, something happens that the stress energy tensor, instead of doing this, effectively does this. So that just outside the radius of the thing that is going to be the horizon of the black hole, whether it's this or this, doesn't really matter, that just outside what is effectively going to be the horizon of the black hole, things screech to a stop, the stress energy tensor screeches to a stop, and instead of a black hole, we get something or other whose size is just slightly larger than a black hole. Well, the first question is, how in the world does it know that there's a horizon there? After all, the horizon takes forever. Well, let's talk about apparent horizons. The problem, of course, is that this room is absolutely stuffed full of apparent horizons. I can take 2 light cones and look at the intersection, and that intersection of those 2 light cones is an apparent horizon. And, locally, one doesn't know that whether that is the apparent horizon for a black hole or is one of these stupid apparent horizons which mean absolutely nothing in space-time, because that basically depends on whether or not this apparent horizon actually closes off on itself. And that's a very non-local question. And all this matter doesn't have time to know that non-local question. But furthermore, if one looks at the stress energy tensor, the effective stress energy tensor, i.e. take G mu nu, calculate G mu nu, and look at what T mu nu is, one gets this horrendous acceleration. In other words, I've got a solar mass body that's collapsing at the velocity of light as it nears the horizon, and it stops within a Planck time. Well, f dx, equals 1/2 v squared if dx is the Planck scale. And, sorry, there's an m in there. Then f has got to be absolutely huge. What kind of f could that be? Could it be a radial pressure? Could this thing start emitting radiation, like sometimes they talk about the interaction of this stuff with Hawking radiation or the acceleration radiation near the black hole? Well, the trouble with any radiation is if it's outward going positive radiation, which it should be if it's going out, that's going to push it more. That's the wrong force. If it's inward going, positive radiation, that's going to stop this. But of course, that just dumps the energy into the black hole even faster. So that doesn't work. It could be outward going negative radiation. But of course, outward going negative radiation, which then would give a pull on there, that negative radiation would get out to infinity, and we could bathe ourselves in negative radiation and violate all kinds of laws of thermodynamics. We wouldn't have to worry about thermodynamics anymore. So I think the conclusion is black holes have to form. Whatever it is, whether or not the horizon lasts for forever, the thing that looks like a Schwarzschild black hole has to form. Pardon? I wonder why. Go ahead.
I just wanted to point to a possible place where one would find a flaw with the reasoning, which looks so obvious, classically. It's a big object, it should form. I think the thing which one might want to think about is that if you look at the path integral, there's a measure and there's a classical action. The black hole has something funny about it, namely a very large entropy, and that big entropy gives a large measure to the path integral, which violates the classical approximation. It's not easy to see that if you look only at the classical term.
It doesn't matter. I mean, the only way in which one could, in fact, get this kind of thing happening is if you really and totally violated Einstein's equations, believe that Einstein's equations got violated just at this situation, just at this horizon, on scales where the radius of curvatures are kilometers, in which we absolutely believe that general relativity is good. And this system has no way of knowing that it's coming anywhere near a black hole, near to making a black hole. That's a non-local statement. So it would have to know about the whole future in order to figure out whether or not it's going to make a black hole.
In support of that comment, that fake apparent horizon has a huge entropy too. Infinite, in fact, since it goes on forever, but it has the same entropy density as any.
Well,
let's
not get into that. One of the other things that then gets talked about is that when we have a black hole which is formed, it is certainly true that it takes light rays longer and longer to get out. In fact, the definition of a black hole is precisely that thing for which light rays can't get out from the inside. So originally, black holes in the Russian literature and so forth were called frozen stars. But of course, the name frozen star was a complete misnomer because they aren't so much frozen stars as completely disappeared stars. Because not only do these light rays take longer and longer to get out, they're redshifted exponentially. So the closer to the horizon that the radiation is emitted, the higher the lower the frequency, and the frequency is rapidly much, much, much bigger than the black hole, much, much, much bigger within far, far less than a second. It's much bigger than the whole radius of the universe. So you simply cannot see anything. But besides that, who cares whether you can see something or not? Do you disappear when I do that? Where's Lenny? The answer is, of course not. The world keeps existing just because I can't see it. And this whole thing comes about because of the peculiar observer that I am, that radiation can't get out. In the little waterfall analogy where you have water flowing from slower to faster than the velocity of sound, the sound radiation from those fish falling over the water also gets base shifted. Does anyone believe that somehow or other that the fact that you can't hear those fish go over the waterfall has any kind of physical significance other than it makes a really nice analogy when you're giving colloquia about black holes? The answer, I think, is we would all believe, come on. The fish falls in. Nothing of that fish is left behind. There's no information that gets strung out over the horizon, etc., that gets left behind to escape to infinity.
That's because the fish went down the drain.
Yeah, the fish went down the drain. So the third thing is black holes radiate. This was, of course, Hawking's discovery. At around that same time, I was also working on, this came about because of trying to understand Stephen Fulling's thesis, where he had quantization in Rindler space, quantization in Rindler space, and quantization in Minkowski space, and he was wondering if they were equivalent to each other. And what I realized is that if one looked at the null rays, both for the black hole and for the Rindler space, that there were two definitions of positive frequency that one could take. One could take e to the I omega u, shouldn't call it positive frequency, but positive norm, because that's really what it is. We had e to the I omega u, where u is the affine parameter along the null ray, and you had e to the I omega little u, where little u is the killing vector along the time-like killing vector along the light ray. These are two possible quantizations. This one corresponds to Minkowski, this one corresponds to Rindler, and the realization that if I take, I've got an e to the I omega u tilde over on this side, because u only goes from minus infinity to infinity on each one of these branches, and that if I take the right combination, there's probably a factor of 2 in here actually, but I can never get these factors right. E to the I omega u plus then e to the plus beta omega over the square root. That this thing times e to the, e to the I omega u tilde, that this thing is actually made up only of waves that go as e to the I capital omega u. So there are clearly two different quantizations, two different definitions of positive frequency. There's a Bogoliubov coefficient between that description and this description, and that immediately leads to radiation. Of course, this has to do with an eternal black hole, and what Hawking showed before I did this, but, well, it's basically going on about the same time, but what Hawking showed is that if you have a collapse, where you, of course, don't have that past horizon, that, in fact, the state that's coming out in this direction looks more like e to the I omega capital U than it does like e to the I omega little u. And that immediately leads to the fact that the black holes evaporate. In a somewhat incoherent fashion, I, in fact, mentioned this at the famous Appleton-Rutherford conference in which Hawking gave the first talk, the first public talk that he gave on his result. And those of you that think unscrambling the information from black holes is something you can do, that means you can actually go out and unscramble all of the information, which will allow you to, again, hear me giving that talk and see the transparencies that I had in that talk, where I mentioned that there were, in fact, two different quantizations that one could have along the horizon, which was exactly referring to this. Unfortunately, in those days, we didn't have the recording and so forth. So this follows this radiation coming out from black holes, follows very, very easily. The radiation is thermal. These omega modes are thermally populated. Yeah. But one of the questions that's arisen all the time is, where does this radiation come from? Now, because of the fact that particles are something which are not an inherent part of the theory, we do quantum field theory. We do not do particle physics. Particle physics disappeared in the 1920s. despite the fact that all kinds of courses are offered at universities called particle physics, if you actually look at what is calculated, they're calculating field theory. And I do wish physicists would get this through their popular heads so that you wouldn't get the insane statement that the force between two electrons is because of the interchange of virtual photons. It's a horrible description. But that's a whole other hobby horse, and if I ride off on that, you'll never see me again. Let's look a little at another test. Let's look at a little model, and I'm going to write down the metric, and the metric is going to be e to the x dt squared minus dx squared. This is in 1 + 1 dimensions. This is for x less than 0. And is going to be dt squared minus dx squared for x greater than 0. Now, this is clearly flat space. And some of you may, let's put a 2 in there. Some of you may recognize that this is just flat space in Rindler coordinates. The usual coordinates, we define rho as being equal to e to the x. And then this is in the usual rho squared dt squared minus d rho squared. So this is Rindler space. This is Minkowski space. In Rindler space, we know that the Minkowski vacuum in Rindler space has a stress energy tensor, a regularized stress energy tensor of 0. And we're pretty sure that that's the right answer because there's not all kinds of funny stuff going on in this room. Similarly, out here, this is in Rindler coordinates. So if I sit at a constant x here, I see a whole bunch of particles. In fact, a thermal distribution of particles. Well, what happens here is I get the energy of the thermal distribution plus the energy of the Rindler vacuum, but this guy is negative. This is, of course, positive, and this guy is negative, and these two guys just add together to give 0. So for the Rindler coordinates, the natural state, the 0 energy state, is to have this thermal equilibrium of particles coming out and going in, as Lenny mentioned. In the external space, the natural vacuum is to have nothing, no particles running around there. Now, let's put in a scalar field into this situation, and the scalar field is going to have the usual equations of motion, except that at x equals 0, there's going to be a mirror, a delta function potential phi squared of x. So it's going to act sort of like a mirror. What this mirror is supposed to imitate is the angular momentum barriers that you get in the 4-dimensional Schwarzschild, 3 + 1 dimensional Schwarzschild solution. Well, what do we know about these mirrors, these delta functions mirrors? At low frequencies, they act like really good mirrors. Everything reflects back in. So as a result, at low frequencies, what we're going to see here is we get an outgoing thermal spectrum. It reflects off the mirror, and you get an ingoing thermal spectrum coming back in. So that just looks like an equilibrium thermal array. But at high frequencies, some of that radiation leaks through the mirror. So we've got the mirror sitting here at x equals 0. Some of the radiation leaks out. Most of it gets reflected. That radiation that leaks out from this side looks like positive energy. So we get a bunch of positive energy going out here to infinity. From this side, on the other hand, we've subtracted a little bit of radiation coming back towards the black hole, i.e., we've decreased the energy in this thermal bath. Now, the energy in this decreased thermal bath is slightly too small to cancel that, and we get a negative flux of energy going back into the black hole. There are two important things about this. What this is telling us is that in this little simple model of Hawking radiation, the radiation has a positive energy flux here, a negative energy flux here, all being created at x equals 0. That's where the radiation is coming from. That's number one. The second thing is that this is a field theory. It's not a particle theory. If we go back and look at Planck's derivation of the Planck spectrum, what he did was he said, okay, we've got this electromagnetic radiation. How does one get electromagnetic radiation? Well, it has to be created by sources. So there have got to be these little sources in the walls of the box that radiate and produce the electromagnetic radiation. As a result, if one thinks about the thermodynamics of that thermal spectrum, one is naturally led to think about also the thermodynamics of these small degrees of freedom that sit inside the walls of the box. But this radiation is not produced by some little sources wiggling back and forth.
So, Phil, you've already drawn a picture where something came out and went back. Why did you draw that picture?
Sorry, which picture?
The hairpin there.
Why did I draw that?
What was that? What did you have in mind there?
There's a mirror here.
Yeah.
There's
What is it that came and went back?
So what came out was I'm describing this in the usual particle physics point of view, that there's this radiation that comes out, hits this mirror, and goes back in. On the other,
Tunnels through.
and some of it tunnels through.
Right.
On the other hand, I know from the Minkowski, this is just flat Minkowski space in the vacuum.
I rest my case.
This is just flat Minkowski space in the vacuum. There ain't nothing there.
I'm sorry, it's not flat Minkowski space. It's this space that you wrote.
Inside, it's just flat Minkowski space in the vacuum state. That's all. If that were a perfect mirror, that's all that's there. Okay?
Then take away the hairpin.
Sorry? No.
Then take away
The mirror, this is a system from the Minkowski space perspective where you have this thing, you have this mirror, which is an accelerated mirror. There's nothing coming in here. There's nothing coming in here. But there's this negative energy flowing out there and this positive energy flowing out there.
Then take away the hairpin.
Yes. In this diagram, I will take away the hairpin. In this diagram, I will leave it because that's from the point of view of the accelerated observer.
Exactly.
But that tells us that trying to think about particles is just the wrong thing to do, because what a particle is depends on your state of motion. Yes? What a particle that is depends on your state of motion. The quantum field theory, of course, cares not in the least bit about how you are going to look at that quantum field. It just acts. And this is how it acts. It produces this flux of negative energy and a flux of positive energy going in the other direction. Why? Well, because the equations of motion of the field have been altered by this mirror, this delta function mirror, or in the case of the black hole, this time-dependent angular momentum barrier in this coordinate system. They've altered the equations of motion, and that alteration of the equations of motion in and of itself produces the radiation. There's no little sources there that are producing the radiation. But this also then is important to think about as far as if one wants to talk about the entropy of these black holes. Of course, one of the hugest surprises, this was something that I certainly didn't foresee, and Stephen Hawking, having been worried about this totally phony thing called the laws of black hole thermodynamics, which made no sense whatsoever without the temperature. No, because of that's the initial state. The initial state was that nothing comes in and nothing comes in from either side. No. I live in space-time. I don't live in any Euclidean. Of course. And the state I'm talking about is nothing comes in from either side. If I switch on this mirror, and we'll get back to that later on. Yeah. So basically all I'm saying is that if I look at the radiation coming in this way from the point of view of a geodesic observer, or I look at the radiation coming this way from the point of view of a geodesic observer, nothing is coming in. That's the choice I've made. So the choice I've made, the initial value choice, so that's why it's not time symmetric, because I chose initial values rather than final. I could have chosen the choice in which I say nothing comes out there, and then I would have had to have radiation coming in from the past. But that would be perverse, because we don't usually think about science in that way. Okay.
It's the Unruh state, not the Hardle-Hawking state, right? I think you're
Yes. Yes.
the so-called.
Yes. That's what people sometimes call it. I don't know why. You realize, of course, that Unruh means restless in German. And I mean, one of the ironies of life is that I got saddled by this name when it doesn't fit me at all. But it turned out to be very useful. I mean, this acceleration radiation, acceleration is certainly a notion of restless. So that's just restless radiation. But in this case, this state is one where the incoming state, there's nothing going on. So it's a very calm state. So this should probably be called the anti-Unruh vacuum. Anyway, enough of that digression. So if one, remember that when one thinks about black hole thermodynamics, this is the crucial equation. The reason we believe that black holes have an entropy is precisely because there's a temperature. And that temperature is proportional to, well, the inverse energy, but as a function of the energy. So it's the temperature that's really the key thing. So if one is going to start talking about the entropy of a black hole, you had better make sure that there's a link between whatever entropy it is, if you are going to regard this as fine-grained, something fine-grained, that there exists a link between whatever that fine-grainedness is and this thermal radiation that gets produced.
Bill?
The thermal radiation is being produced just by this change of motion of the scalar field. It's not being produced because there's some sort of wiggling going on there. It's purely produced at low frequencies, at low energies, by this behavior of the metric. In fact, in the 1 plus 1 dimensional example, this is just the derivative of the Ricci scalar, is what produces this radiation as a long wavelength thing. There's nothing fine-grained going on there. If one is going to describe the entropy of the black hole, somehow that has to link directly, not via some convoluted argument, to the thermal radiation that's given off, to the source of the thermal radiation that's given off.
Bill,
And none of the fine-grained explanations for entropy, for me at least, come anywhere close to doing that.
So we have some big mysteries about how this works, but you say that the reason there's an entropy is because of this relationship.
Right.
But really a black hole is a big system with whatever they are, a lot of internal degrees of freedom. Why?
No, a black hole has no internal degrees of freedom. The no-hair theorem of black hole thermodynamics precisely tells us that black holes don't do anything. They have energy, they have angular momentum, and that's it.
From the point of view of the outside, but there's all this stuff that fell in.
There's all the stuff that fell in, and that all crashed into a singularity, and that was it. Bye-bye.
I won't debate that now.
All right. I'll mention a little bit about some of the other possibilities, but.
Sorry. So then the second law of thermodynamics, as proven from general relativity, is a coincidence from this point of view.
Yeah.
A miracle. Why is it true then?
I don't know. I mean, it is. I agree that it's a miracle.
It's very surprising, right? I mean.
Yes, I agree. I'm not in disagreement with that. It certainly is surprising, and I certainly believe in it. I mean, Bob and I, way back when, wrote this story in which we actually argued that you could run heat engines off of this black hole, and those heat engines behave exactly the way one would expect a heat engine to behave for an ordinary matter system. But that doesn't mean that the entropy of this thing has to be the same as the entropy that we got used to from Boltzmann and Maxwell and Gibbs and so forth, that is due to the fine-grained atomic structure of whatever it is that holds the entropy. Remember, entropy was invented long before Boltzmann and Gibbs and Maxwell and so forth to explain the operations of engines.
Right, but it was progress when,
Yes, in many situations it turned out to be progress. The question is whether in this totally new situation it is. And I'm basically agnostic. I don't know. I mean, there may be. Yes, I am. Unfortunately, there are other people who are so strongly on the other side that they tend to push one just to, it's like somebody lassoing you with a long rope. You're trying to.
Push you? Are you kidding?
You're trying to stand at one point, and you've got this guy on a horse trying to pull you off of it. You've got to pull back in the other direction. Well, I do get very hot when this happens. So anyway, none of the proposals that I've seen do this link between the temperature, between whatever it is that's causing that thermal radiation, and their attempts to explain the microstates of the radiation. This suggests strongly, in fact, that whatever explains the entropy should be something that's well outside the black hole. Not something on the horizon, not something deep inside the black hole, but that sits well outside the horizon of the black hole. Do I have a suggestion? No.
Entropy. That's where the thermal radiation comes from.
No, it doesn't. The thermal radiation simply comes, as if I look at the stress energy tensor, the thermal radiation just comes from this angular momentum barrier, roughly around r equals 3m. That's where the thermal radiation comes from. If I go ahead and take the viewpoint of some accelerated observer outside the horizon, then I can start talking about these things called particles, which have no place in quantum field theory. But I talk about these particles, and I can cast this story about.
But Bill,
Yes.
you can mine.
Yes, I agree.
You can mine the rest of the radiation all the way to the horizon.
Yes.
And so what the entropy has to be telling you is, what's the maximum thing you could mine?
I don't have a final answer. And there's certainly a secret here. But one of the things that I'm sure of is that once one chases a wrong answer and convinces oneself of a wrong answer, one's never going to look for the right answer. If one looks historically at the problem of both of radiation and the problem of ether and so forth, there was a huge effort expended on trying to understand how the ether actually behaves. It had to exist. How does it behave? And in fact, there was this huge excitement because it was realized that if you started looking at these little vortices and knots and so forth in the ether that you could explain matter. That's what matter was all these little vortices in the ether, and you had a huge industry of people extremely excited, making statements like, this is so interesting, but it's going to take us at least 20 years to figure it out because the mathematics is so complicated. And it turned out to be entirely the wrong direction to go galloping off in. And huge amounts of efforts were spent on that. Another thing, we've all heard sermons preached from the pulpit, the physics pulpits, that if we allow black holes to lose information, that would lead to the collapse of Western civilization as we know it. That physics would have to stop, and we would all have to give up our jobs and become ditch diggers. Lenny introduced the metaphor of war into this conversation. And unfortunately, what these sermons remind me most of is the statement a number of years ago that unless the Western free world invades Iraq, we would be having a minaret on every street corner looking out over a nuclear wasteland of America.
Bill, you would make a fantastic preacher.
My grandfather was a preacher. One of the arguments, for example, that was adduced for this disaster was the non-conservation of energy. That if you were to allow black holes to become decoherent, that would destroy energy conservation, and we would get these explosions of the order of 10 tons of TNT occurring randomly, and that's about 1 Planck scale of energy, occurring randomly in this room or wherever, and we might have noticed that if that occurred. And it doesn't occur, and therefore black holes can't lose information. Unfortunately, that link between energy conservation and decoherence is a common myth even in condensed matter systems in which they really do work with things where they can measure the decoherence and measure the energy. But there's a very, very simple counterexample to this. Now, I want to warn you that all this is a counterexample to the statement that decoherence always leads to energy non-conservation. Yes? Yes? That's true also. It's true also of this. Let's take, well, no, I'm going to take a simple example that I can actually calculate. So two particles whipping towards each other, and they suffer, this is 1 + 1 dimension, they suffer a delta function interaction. But the strength of that interaction depends on a whole bunch of spins. The x component of spins, which only, these are in some internal space. If you want to think about black holes, these are the inside of the black hole or whatever. These two guys come together, they scatter, and what you find is that the scattering of these guys turns out to depend on what the internal state is. In particular, if I put that internal state into a z, sigma z equals +1 eigenstate for all of these internal spins, then what I discover is that these reflected rays, those particles sometimes just go through each other, sometimes they bounce off of each other, and those reflected rays, in fact, are incoherent once one traces out over those spins. However, because those internal spins carry no energy, the spins are coupled to the field, but the spins are coupled to the particles via that delta function interaction. So while the interaction is going on, certainly the spins pick up have an energy, and they cause the spins to rotate.
There's nothing in the Hamiltonian that doesn't commute with the sigma x's or sigma
Right.
z's. Okay.
Right.
That's rather exceptional.
So Bill, and this is partly an answer to Tom's question. If you attempt to turn this into a field theory model, where you have these things that that commute with the Hamiltonian, as Lenny was asking about, what you get is something very similar to the old alpha parameter story of wormholes.
Yes.
And then you can describe what is a apparent loss of information for a while, but not a repeatable loss of information that could describe the successive experiments of forming black holes and letting them destroy information.
Right now, I do not care about that. Right now, the only purpose of this example is to break in your mind the link between decoherence and energy conservation.
It was an imprecise link. And that's the point.
Sorry?
That was an imprecise link.
Yes,
and that's
it
the
was
point I'm
definitely an imprecise link, and that's the main point I'm making. That's precisely the point that I'm making. And that's the only thing that one can draw. I'm not claiming that this looks at all like black holes, that this is how quantum gravity is going to work, that there are going to be these internal spins or whatever. Now, in condensed matter physics, Philip Stamp, the dominant model of decoherence had been the harmonic oscillator model of decoherence, in which the environment was a bunch of harmonic oscillators, the so-called Caldera-Leggett model, and one interacted with that environment, and one found a very close link between energy loss and decoherence. So strong that everybody thought that this was a theorem, including using the result of these guys' results. When Philip Stamp came up with an alternative model of decoherence, the so-called spin bath model, in which the bath was a whole bunch of spins, he basically showed, again in condensed matter systems, that there was no necessary link between decoherence and energy conservation. So the only purpose of this model is to break that link in your mind.
Sorry, let me
It may be true that for black holes, I don't know, it may be true for black holes that there is a link between energy conservation and decoherence. It may be true that that's only right for big black holes, but not for little black holes. There are all kinds of possibilities. And if 1/100th or 1/1000th of the intellectual effort that has gone into the unitarity push had gone into really trying to understand these systems, I think we'd be a lot further along. It's starting to sound like a sermon, isn't it? Let's get to firewalls. I'm running out of time. What can I say about firewalls?
Before that, just one more iteration on that. So it's true that there is an imprecise link, that you said it. But if you try to make a precise link with the kind of physics that's losing information that you want to model, I think that you do find that you have problems. If you have decoherence, you have loss of energy.
I don't know. I mean, black holes are exactly the kinds of things that if you look at them from outside, the interior of the black hole has zero energy. Because time, as far as you're concerned, time doesn't flow for the black hole at all. So it's exactly like these spins, which have no internal Hamiltonian. They don't evolve in time. Similarly, for the outside observer, whatever is going on inside the black hole really has a zero Hamiltonian. And it's only in the interaction, the emission of the radiation, and the absorption that there's some sort of time dependence going on there.
Well, we had one model of this kind of thing, which was the space-time wormholes, which we knew in the end, we found in the end, did not lead to the kind of loss of
Well,
information
there were,
that we
there were.
described.
Let's not get on to that. There were a whole bunch of assumptions that went into that argument as well.
Let me understand better your statement. So, I mean, this delta function interaction induces a Hamiltonian for the other guys, right? For the spin.
Yes. So when the two particles are sitting on top of each other, yes, certainly the inside evolves. And it's that evolution of the inside that produces the decoherence.
If we had two particles in a constant, in a wave function, which is more or less constant.
No, this was all done quantum mechanically. This wasn't classical. Right. I solved the Schrödinger equation.
So if you have two particles with both of them in a constant wave function, don't you induce a Hamiltonian?
Two particles with wave functions, wave packets, two particles came along, they interacted, they separated. The separate system has an entropy, not very much, it's about 1 bit of entropy in the model that I did. But on the other hand, this interaction is an instantaneous interaction. The particles go through x equals x primed in 0 time. Well, it's of course not quite 0 time quantum mechanically and all of that, so that they do have enough time to allow the internal spins to rotate to produce the decoherence. Black holes take 10 to the 53rd years. They sit there and whatever is going on. So they've got lots of time to do lots of decoherence. And since their energy on the inside energy, all of the energy of the black hole is in the gravitational field outside the black hole, the internal energy is all 0. So when the thing evaporates, you still get a complete energy conservation for these black holes. That's the kind of story that I would tell. I mean, obviously there are a lot of, but then again, in this crowd, telling stories with no support is the way it's done. Firewalls. What can I say about firewalls? Well, not terribly much, but let me try and say a couple of things. One of the problems that I've been looking at recently is the accelerated sponge. You know, you've seen those Bounty commercials where they have their Bounty with sponge pockets wiping up the mess. Well, we all know that there's no bigger mess than a thermal distribution. That's the maximum mess that you can have for a given amount of energy. And we also know that an accelerated observer sees a mess, thermal spectrum. Can one use a sponge in order to sponge up that thermal mess? And the answer is yes, and I use my favorite model, which is a one-dimensional scalar field. So I've got a one-dimensional scalar field, phi of t and x, in space-time with a metric dt squared minus dx squared e to the 2x. So this is Rindler space. So this sponge is at a fixed location in Rindler space. But the quantum field is at a fixed location in Rindler space, and this is going to be my mess. But a sponge needs what Bounty calls sponge pockets, namely places where you can put the mess. And my sponge pockets are going to be another scalar field in an internal degree of freedom, because sponge pockets are inside the sponge, that I can call theta, which obeys the internal metric is just the flat space metric. And I now get an interaction which looks like A times delta of x times phi squared of x plus twice B times delta of x, delta of theta, phi of x, psi of theta. So this is an interaction between the sponge and the sponge pockets plus c times psi squared of x. Theta, delta of theta. So if it were just a delta of x, this would look like a mirror, or a delta of theta would look like an internal mirror, but this is the thing that couples them. In particular, it turns out that it simplifies the equations no end if one chooses those coefficients such that AC minus B squared equals 0. And what you find is that the sponge absorbs radiation, absorbs the thermal radiation. So I've got the sponge sitting here, I've got this thermal radiation coming in, because this is an accelerated sponge and I'm in Rindler space coordinates. And some of this radiation goes up in the theta direction, because it gets absorbed by the psi of theta. Equivalently, of course, the psi of theta comes in and radiates out so that you preserve unitarity. But the theta, I'm going to assume, is in its vacuum state, and the sponge is not in its vacuum state, is in this thermal state. So this thing is going to absorb thermal radiation and emit basically vacuum. Well, we know that the argument that we had before, this is going to produce this negative flux of radiation forever coming off the two sides of the sponge. That's a nice way of producing negative energy. But now the question is, if we look at it from this point of view, we've got this negative radiation coming off here. What happens if I switch on this sponge? Well, before I switched on this sponge, I had this, looking at it from the Minkowski point of view, I had the vacuum scalar field coming in from both sides. After I switch in this sponge, much of that vacuum was absorbed, and what gets emitted here is now scalar field from the sponge pockets is being given off here. And the important thing about that scalar field from the sponge pockets is precisely that it's totally incoherent with respect to this scalar field in the vacuum space over here. So what I get is I've got a quantum field, of course, being given off by the sponge, which acts exactly like the quantum field I ever started with. But I no longer have as much coherence between this field here and this field here in the vacuum. If I were to make the internal field of the sponge a thermal state, what I would find out here was that I would get zero energy being given off by the sponge, not a negative energy, because I'd still have that thermal balance completely given off. But what I find is that no matter how I do things, at the point at which I switch on the sponge, i.e. A and B and C are switched on from zero, I suddenly get this loss of coherence between the radiation given off by the sponge just afterwards and the radiation that's traveling in the space-time before, and I basically get this firewall of positive energy radiation. Well, in fact, it had better be positive energy radiation, because if there was vacuum inside, this is all negative energy, and we know that the total energy integrated over a complete slice had better be equal to zero. So these guys give off these massive positive energy fluxes. If I now boost this so that this occurs way back at the initial, at t equals minus infinity, then I find this singular delta function squared, at least, singularity in the stress energy tensor traveling just along this past horizon. And I get a firewall. And that firewall is arising precisely for the same reason as the firewall arises in all of the discussions, because there's this loss of coherence, this loss of entanglement between the radiation that's given off by the sponge after it switched on versus the radiation that was there before it was switched on. In fact, I've come to the conclusion that firewalls are, in fact, almost ubiquitous. Let's ask another question of the same kind of model. I go ahead and I put now not a firewall, not a sponge, but just a mirror. So this is just a delta of x, phi squared delta of x, and we notice that that obeys that AC minus b squared equals 0, because c is 0 and b is 0. What happens? I now want to ask the question about the Hartle-Hawking vacuum. Does there exist a Hartle-Hawking vacuum for this? Now, one of the assumptions that gets almost universally made is, yeah, of course. I mean, Hartle-Hawking vacuums, they're just the equilibrium state. But we notice that there's a problem even with the equilibrium state. If that internal guy emits radiation such that the outside world is still in thermal equilibrium, we nevertheless get the singularity along the past horizon. And the answer is, although I haven't been able to completely prove it, is that remember, this situation is completely boost invariant, that there exists no state which is regular along both horizons and is boost invariant. I.e., typically one gets this firewall occurring along, for example, the past horizon, but it can equally be along the future horizon. If one puts an exactly symmetric mirror on the other side, then I suspect that there is a regular state. Again, I haven't been able to prove it. If one makes this mirror slightly weaker than this one, again, you have trouble. One of the things about these mirrors is that they're good mirrors only at low frequency. At high frequencies, they become transparent. So it's not really simply an ultraviolet problem. That there's something more going on. Now, these mirrors only fall off as basically 1 over omega squared. The reflection in the energy falls off as 1 over omega squared rather than, let's say, exponential, which would be nice. But I haven't done the calculation or been able to figure out a model such that it falls off faster to see if that makes a difference. Okay. One of the things I wanted to report on was, and it turned out to be very apropos, is that in fact Jim Bardeen has recently been thinking a lot about the whole firewall issue and black holes. And one of the ideas he came up with was, let's assume that at the center, at the singularity isn't really a singularity, but is some finite point in space. So instead of 1 minus 2m over r, we have the central metric looking something like this. This is a metric that when r is very small, this term dominates, and this is just 1 minus r squared over a squared, which is de Sitter space. So A could, for example, be of the order of the Planck scale. M is the mass of the black hole. And if we write this in retarded coordinates, minus r squared d omega squared. If we write this in retarded coordinates, we can in fact get a solution, a nice solution, with null radiation just by making that mass be the null coordinate v, depend on the null coordinate v. This is basically the Vita metric, and it's got a bunch of energy coming in towards the black hole. And if we make that energy flux negative, which you expect for a black hole, then this thing will gradually decrease this value of m as though we were evaporating the black hole. One can match this onto, so here's, r equals 2m, sits out here, getting gradually smaller. One can take, let's say, r equals 3m, and match this Vida metric onto another Vida metric, an outward going Vida metric, where you get positive energy radiated out to infinity, and that this system now obeys all of Einstein's equations, non-singular everywhere. Pardon? What's happening at the join? Well, there's a delta function, whatever, going on at the join, but that's supposed to represent remember the radiation is created by the angular momentum barrier. So I've made the angular momentum barrier here be a delta function, but I could smear this out as well. I would just get a much more difficult metric to solve. Okay, but that's not going to, smearing out this thing will then make the stress energy tensor regular everywhere, but it doesn't really change any of the physics. Well, what this does is that eventually this system is always regular on the inside. Eventually the mass on the inside becomes small enough that if we look here at small r, we get 1 minus r squared over a squared. There's a horizon in there. That's a Cauchy horizon. And at roughly r equals 2m, there's another horizon, which is the usual Schwarzschild horizon, or at least there's a point where this thing goes to 0. Well, those turn out not to really be horizons. They're sort of like apparent horizons. And so what we get is we get an r equals 0 here, and we get this pair of horizons develops, grows when the black hole forms, and then they come together, and you get a system like this, and eventually we just get flat spacetime. There's no actual horizon in this thing because everything on the inside eventually can get out. The light rays inside here tend to do this. And the light rays inside here tend to do this. And finally, when this apparent horizon disappears, they escape. So he's advanced this as an explanation for the information paradox because, the Hawking radiation gets produced here, the partner falls in, stays inside the black hole forever, and eventually escapes. Now the firewall argument doesn't work because, the firewall argument usually is if we want quote-unquote unitarity, we go from here to here. We have to have perfect entanglement, but we also have to have perfect entanglement here. Otherwise, we get this delta function, delta squared function in the stress energy tensor. And so that gives us the firewall. Well, here, this radiation and the stuff coming out way back there is the same thing. So this can be correlated with this and be correlated with this without causing the necessity of a firewall. Yes?
How much energy comes out of that last bit with...
Well, this model has got a lot of problems, which I think is...
Or a lot?
Tiny.
Good. Okay, so all this information is coming out...
So all of there's two problems here. Number one is that this Cauchy horizon is an attractive horizon like the white hole horizon that Doug Erdely studied 30 years ago, which is highly attractive. Everything falls onto it. And you just get this massive singularity more or less sitting there along that horizon from all these fluctuations. The second thing is, of course, that all of this information has to flow out, but all of the mass of the black hole is evaporated, so you need loads and loads of information with very little energy.
That means very long wavelength quanta.
Yeah, but that... Pardon?
They must come out in extremely long wavelength quanta.
Somehow, well, whatever.
It's a long-lived remnant then.
So there has to be virtually no energy in this stuff, at least once it gets out to infinity. Who the hell knows what's going on right here? At least when it gets out to infinity, it's got to carry virtually no energy, but a lot of entropy. Now, Bardeen gets around this by saying, well, perhaps A grows. A is also a function of V for some reason. And it keeps growing in such a way that this loss of the horizon occurs when the amount of mass left is still, let us say, half the mass of the black hole. He has a little formula where that the rate of change of A is proportional to 1 over m squared, is it? Well, anyway, it's proportional to some function of 1 over m, and then he finds that the two horizons coalesce well before all of the energy has been radiated.
Is the second half of the radiation entangled with the first half?
Yes.
It is.
Sure, I mean, all this radiation is all entangled with this stuff because it's exactly the partners that were entangled. So that entanglement gets held. This seems to be very much the kind of model that Stephen Hawking was, in fact, suggesting in his talk. It has a lot of problems, but I think one of the things that's astonished me most of all in this meeting is that the claim is that people wanted to hang on to so-called unitarity, which meant that from before to long after the black hole evaporated, that there was a unitary relationship between that. Why did they want unitarity? Well, it's not because of probability, because the S matrix that Stephen Hawking originally suggested also preserves probabilities. So there was some internal gut feeling that this unitarity had to be held onto, and it's claimed because of quantum mechanics somehow. But one of the things that has depressed me no end was that constantly people are getting up and telling us how they're going to tear quantum mechanics to tiny little shreds in order to preserve this goal of unitarity. And unfortunately, this again, in Lenny's frame of the war analogy, reminds me of nothing more than General Westmoreland during the Vietnam War, standing outside a village in which and the village was a smoking ruin behind him, and he said on national TV, well, we had to destroy the village to save it. And that's what this tearing apart of quantum mechanics in order to save unitarity reminds me of. At this point, I better end my sermon. And fortunately, my airplane is leaving very soon. So I'm also going to be running.
Amen.
So I have about 5 minutes.
I just wanted to comment that, how do you think of the information that's radiated from something like article 3M?
Right.
I mean, you do escape from many of the AMP's arguments. I think the main thing that stands in the way, though, are these mining arguments. So,
right.
So if there would be some, unforeseen complication in trying to mine the information from farther into the zone, I think then we would have more of an escape here.
Well, one of the interesting features, I mean, somebody asked me a question when I was at Perimeter, Sandu Popescu. He said, how do you know that there's a black hole and something hasn't just almost collapsed to become a black hole? And I started thinking about that and thinking about what happens if you had a black hole and you stuck another shell of matter just outside its Schwarzschild radius. Not the Schwarzschild radius of the black hole that's already there, but the Schwarzschild radius you would have if you added this mass to the black hole. Well, what happens is, of course, as you assemble this, there's all kinds of junk comes out, radiation comes out, but then the temperature drops of the black hole. And the closer you are to the horizon, the lower the temperature of the radiation that comes out. So what that suggests to me is that in this mining, one really has to do it properly, take into account not just the surrounding space-time, but also the effect on the gravitational field of this mining apparatus that one is lowering into the black hole. And that it in itself changes where the particles are being created by the very process of your mining it.
I'd just like to stress that even if we didn't go in and mine, all of these high L modes have some probability that's not zero to tunnel through the angular momentum barrier.
Yes.
So their wave function is going to develop a tail outside of the black hole. And if we assert that these are in the Hawking state in the infalling vacuum, then that alone would destroy unitarity, if only by a little bit. You don't have to
I don't mind unitarity being, I don't think there's anything terrible about unitarity being destroyed.
I know, but why did you give such a long talk in that case? I mean, if we don't worry about unitarity, there don't need to be firewalls. That's it.
So,
fine. You just summarized my talk, although I did say a few other things along the way. But.
So,
yes.
In response to the last interchange, I wanted to mention that that's the kind of model that, for example, I have been exploring, where the information is emitted further out than right at the horizon. And I actually think that there are models that evade at least the objections I've seen that come from the mining Gedanken experiments. And I'll talk a little bit more about those on Wednesday. But basically, you can have extra interactions that only excite information-carrying excitations going out when you are mining, and when you're not mining, they're not excited. So more on that later.
Okay.
I had a question.
I'm sorry I won't be here.
I had a question about your final model that you presented. If I understood it correctly, it doesn't have a...
That's Bardeen's model. That's based on Frolov and Novikov in the 70s. And then Bardeen had this idea, and then Scott Hayward developed it. And
So
then Bardeen has been working on it later. So just to give the, it's not mine.
If I understood correctly, it doesn't have a global event horizon.
Right.
So could you comment on the relation of that to your opening comment that black holes form?
The event horizon, I mean, by black holes form, I mean something that looks like it has the metric of Schwarzschild. By horizon, one means a region which will never, ever, 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 no matter what you do, communicate with infinity. That, of course, depends on what happens infinitely far into the future. So by a black hole, I mean something that looks like a black hole now, that all the tests that I would run on it now would make it look like a Schwarzschild black hole.
So in particular, you wouldn't distinguish between something which has a global event horizon and a compact bound state, which is essentially a perfect absorber?
Would I differentiate between them? I don't know. It's, the metric is certainly part of what I would call a black hole.
Let me make a comment. The speaker has to leave at 12:25 sharp. Has his flight. So there's 5 minutes left for questions. All right.
The taxi's waiting. He's blowing his horn.
Bill, first of all,
I'm leaving on a jet plane. Yes.
First of all, thank you for some extraordinarily interesting examples of very interesting things. I really love them. In particular, I love the example of the decoherence without energy violation. But I think if I had seen these particles come and collide and do that and conserve energy and decohere in this way, my guess would be there's a spin somewheres, and that spin somewheres is containing the information about, I would guess that somehow, and I would be right in your case.
Of course.
So I am guessing then, if I were to see the same thing outside a black hole, I would guess that I would guess there are microstates of the black hole containing that information. So what I'm saying is your example is a beautiful example.
Sure.
Of what, though?
There certainly, when the matter falls in, If there's a singularity, then all of the information, all those microstates in the matter just fall off the singularity.
The which? The what? The microstates.
Microstates of the matter, etc., simply fall. All the information just falls off the singularity. The black hole doesn't notice this. It doesn't care. It still behaves in exactly same way. If instead of having that singularity in there, you had some sort of baby universes branching off so that all these microstates went in there, that also wouldn't make any difference to what's going on the outside.
Well, okay, but the black holes.
In other words, what's going on inside really doesn't matter as far as the behavior of the black hole.
The black hole has to somehow record in a way that has a memory which of the states.
No.
Well, all right, but
why does it? All it has to remember is there's a mass and angular momentum.
I'm just arguing by example. The example being yours. That spin is the thing which remembered.
In the case of the black hole, the matter itself remembers its own state. If it falls off a singularity, that's the end of it. Where this information is recorded, I don't know, and I really don't care.
Okay.
I'm saying that the behavior of the black hole is independent of, I don't care, not because I'm just so perverse that I don't care, but because the behavior of the black hole is independent of where and how that information is recorded.
Okay, so
where, it's somewhere inside, it's inaccessible, and that's all that matters.
The only last comment is that a good part of the reason that we believe what we believe is by examples that have come from things like ADS-CFT, from matrix theory and so forth, where we can't just dismiss those. A black hole in anti-de Sitter space, right?
Agreed.
Okay.
I mean, ADS-CFT is something that really does bother me. Right. The trouble is I don't understand it well enough. I think there's from my position, I think that there's something wrong in the example. For example, that the link between the interior space and the surface is highly non-local in time, in which case the boundary theory can be as unitary as it wants, and that has absolutely no implication about the unitarity of the interior theorem. Right. That's one possibility. But I don't know ADS-CFT well enough that I can look at it and say, look here, Lenny, you forgot this.
Right. Thank you in any case for reminding us to be humble.
We'll resume in this room at 2 sharp because we have to give the room up at 3 sharp.